Hello, welcome to lecture 17 of the course. In this course so far, we were confined to the discussion of the two-state or two-level quantum system only. In this lecture, we are going to discuss the phenomena of electromagnetically induced transparency, which involves the discussion of three-state quantum system or three-level atom. So let's begin. All of us know that when an electromagnetic radiation or wave passes through a medium, mostly its amplitude or energy get decreased due to absorption. For example, say an electromagnetic wave is incident from the left on a medium, and as it passes through the medium at the output end, the transmitted electromagnetic wave, as you can see, its amplitude is getting decreased from that of the incident one, and it happens due to absorption. Sometimes what may even happen is that the electromagnetic that is getting incident on the left is not going to get transmitted at all due to high absorption through the medium. So at the output end, there is no transmitted wave. All right, so for example, you know that if a laser radiation with appropriate frequency is getting incident on a two-level atom, then if the whole laser radiation energy is getting used to take the atom from the ground state to the excited state, then you are not going to get a transmitted laser radiation. However, there is a quantum mechanical effect called the electromagnetically induced transparency, in short called EIT, where in the presence of another wave called the pump wave. So this actually goes like this. Suppose you have this medium here, and apart from the incident wave, which is known as the probe field, if a very strong field is also incident on it, then in the presence of the strong field, the probe field is not going to get absorbed at all as it propagates through the medium, and it passes through the medium without getting absorbed. That means it is for this probe field, the medium appears to be completely transparent. So this phenomena is the so-called electromagnetically induced transparency phenomena, because it is induced by the presence of the strong field, and it happens generally in the not in two-level atom but in three-level atom. What happens is this, that say we have a three-level atom like this. It has this energy level, say K1, K2 and K3, and if the probe field is applied between the energy level 1 and 3, say this is the probe radiation or the probe field, and if another field which is a strong field, that means it has a strong intensity, a strong field also called pump field, if it is applied between the energy level 3 and 2, then in the presence of this strong field or the pump field, the probe field is not going to get absorbed at all as it passes through the medium, and for the probe field, the medium is going to would be kind of a transparent medium. Okay, and this is what the essence of electromagnetically induced transparency is. So electromagnetically induced transparency refers to the phenomenon where a probe field in the presence of a strong pump field passes through a medium without getting absorbed at all. So we are going to discuss it in some details in this class. However, before I do that, let me talk about the phenomenon of absorption in a linear medium and discuss it using the so-called classical electrodynamics. So let's say we have a linear medium like this, and say this is a linear medium, and this linear medium is characterized by the so-called electrical susceptibility chi. I will come to this fact why I am talking about susceptibility soon. Say this medium has a length L, and an electromagnetic radiation is incident on the linear medium and say this electromagnetic wave is a plane electromagnetic wave and it is propagating along, say, along the z direction, and this electromagnetic wave is polarized along x direction. It is linearly polarized and its amplitude is, say, E0, and as it passes through the medium, so this is the wave, e to the power I kz minus omega t. It has this angular frequency omega. K is the magnitude of the wave vector of the electromagnetic wave. Now this linear susceptibility chi appears due to the fact that when this electromagnetic radiation is going to interact with the medium, it is going to induce polarization, which is basically the number of dipole moments per unit volume, and it is associated with the linear susceptibility chi via this relation. So I am sure all of you know this. And another important quantity which characterize a medium is the so-called refractive index, and this refractive index is associated with the linear susceptibility or susceptibility, electrical susceptibility, by this expression. And if this susceptibility is not very high compared to 1, then we can write the refractive index as 1 plus, say, 1/2 of chi. Okay, and this susceptibility is a complex quantity, so because of that this refractive index is a complex quantity, and I can write it as n is equal to, say, 1 plus 1/2. Susceptibility has a real part and an imaginary part, and because of this I can therefore write that refractive index n has a real part and an imaginary part, and the real part of the refractive index is 1 plus 1/2 of real part of the susceptibility, and the imaginary part of the refractive index is simply 1/2 of the imaginary part of the susceptibility. So the key point to remember here is that the imaginary part of the refractive index is associated with the imaginary part of the electrical susceptibility. Now, inside the medium, the electromagnetic wave is going to be of this form, say E is equal to, it is x polarized, linearly polarized, and you have this k is equal to, k is the wave vector, that is omega by c into refractive index. So this I'm sure all of you know. Let me tell this, that this wave vector or wave number is omega by c. In free space it is simply omega by c because refractive index is equal to 1, but in the medium you have this n. Now this refractive index as is as a complex quantity, so therefore I can write inside the medium the electric field is going to be e to the power I have omega by c nr z minus plus I omega by c niz minus omega t. This I can write as x cap, this is the polarization, electric polarization. Just don't get confused with this polarization. This capital P is the dipole moments per unit volume, number of dipole moments per unit volume, and here I can write it as e to the power minus omega by c niz, right? And I have this part here, I omega by c nr z minus omega t. This represents the propagating part, and this is the amplitude of this electric field inside the medium. As you can see, the amplitude is getting decreased because of this exponential factor here. And in fact I can write about the intensity as well. Intensity inside the medium for this electromagnetic wave, I can write it as I0 e to the power minus alpha. Suppose the distance the medium length is L, so after a distance L the intensity is going to be this one, and you can easily figure it out that this quantity alpha, which is the absorption coefficient, it is equal to 2. You just have to take the mod square, so you have 2 mod square of the electric field, so you are going to get 2 omega by c into Ni. Ni is the imaginary part of the refractive index, and in fact I can also write in terms of the susceptibility as omega by c into chi I, imaginary part of the susceptibility. So as you can see, the important point to note here is that this absorption coefficient alpha, this absorption coefficient of the medium is dependent on the imaginary part of the susceptibility of the medium. So this is a important fact that you should keep in mind. Okay. Now let me talk about this is what I have so far talked about is due to the classical electrodynamics, from where you see that absorption coefficient is associated with the imaginary part of the susceptibility, and if the imaginary part of the susceptibility is 0, that means if the susceptibility is completely a real quantity, then there is not going to be any absorption. At this point, let me talk about what about the quantum mechanical treatment. Well, as you have already seen that the susceptibility is responsible for absorption, which is actually associated with the polarization P via this relation epsilon 0 chi E, right? And as I have already told you that P is, this is the polarization, and it is number of dipole moments per unit volume, where n is the number of atoms in the medium and v is the volume. And in the context of quantum mechanics, already you know that for every physically observable quantity there is a corresponding operator in quantum mechanics. So polarization is going to be represented by an operator. If I go over to the quantum mechanics, so P would be, this is the moment, it is a polarization operator, and this is equal to n by v, and this dipole moment is going to be replaced by this dipole moment operator. Now the dipole moment is a measurable quantity, and we find its expectation value. As you know, an expectation value of the dipole moment operator is we can find it out by finding the trace of rho into density matrix into the dipole moment. Okay, that you already know that this is how we can find out the expectation value of the dipole moment operator. And if I consider a two-level atom, for a two-level atom we have this rho density operator or matrix. I can write it in the form, this form, rho 1 1, rho 1 2, rho 2 1, rho 2 2. On the other hand, the dipole moment operator in the matrix form, I can write it as, so its diagonal elements are 0, as we have discussed in an earlier class because of the parity issue, and we have this off diagonal element mu1 to mu21. So if you actually take the product of the density of matrix and the dipole moment matrix, this matrix form, and you can easily calculate the expectation value of the dipole moment operator. You just have to take the trace of rho and mu, the dipole moment operator. Then if you do the calculation, you are going to get rho 1 2 mu 2 1 plus rho 2 1 mu 1 2, or simply you can write it as rho 1 2 mu 2 1 plus the Hermitian conjugate, right? So essentially what you see, that ultimately this particular term rho 1 2, this is the coherence term, this is responsible for this dipole moment, which in turn, this dipole moment operator gives rise to susceptibility, and ultimately it leads to the phenomena of absorption. So the key point here is to note that you have to look for the coherence term or off diagonal elements in the density matrix elements. Now let me look into the phenomena of absorption in the three-level atom. So we have this, say, three-level atom like this. Here the probe field is applied between the energy level 1 and 3, So this is the probe field, this is the probe field, uh, and the control field or the strong field is applied between the energy level 3 and 2, and there is no transition between the energy level 1 and 2. This transition is forbidden. Between 3 and 2 there is a control field or a strong field is applied. Okay, now this probe gets absorbed in the absence of the control or the strong field. However, in the presence of the strong or the control field, this probe field is not going to get absorbed. And to actually understand it, you can necessarily get it that maybe you will be able to guess that which density matrix element you have to look for. Obviously the density matrix that you have to look for is rho 1 3. Okay, this density matrix is going to be responsible for the susceptibility with respect to the transition between 1 and 3. So this is the term that we are now going to look at. Now first of all, what we have to do is to write the density matrix equation for the system, and the mathematics involved is straightforward but lengthy, and I am going to rush you through the mathematics now. Let us begin with a 3-level atomic system in lambda configuration. In this configuration, we have 3 energy levels. This is the ground state K1. Then there is another energy level which is not much different from the ground state, energy level represented by K2, and there is a third energy level excited state, that is K3, and the probe field is applied between the energy level 1 and 3, and the pump field or the control field is applied between the energy level 3 to 1. And as you can see from the configuration, why it is called the lambda configuration, because as you can see this has the structure of a lambda, right? So that's why it's known as the lambda configuration. And this probe field has a frequency omega p, and the pump field or the control field has a frequency omega c. This is the pump is applied between energy level 2 and 3, and the pump field has an amplitude, electric field amplitude is EC, and the probe field has the electric field amplitude is EP. Okay, now again the energy associated with the ground state is E1, energy associated with energy state K2 is E2, and energy associated with K3 is E3. Now for simplicity, we are going to set the ground state energy to be equal to 0. So E1 is taken to be 0 for convenience without losing any generality. Then the difference between the energy of the second excited state and the ground state, E2 minus E1, is going to be equal to h cross omega 21. Omega 21 is the transition frequency, angular transition frequency between the energy level E1 and E2, and because E1 is set to be equal to 0, so E2 is simply equal to h cross omega 21. This is what we are going to use later on. And similarly, the difference between the energy level E3 and E1 is h cross omega 31, and omega 31 is the transition frequency between the energy level 3 and 1, and because E1 is equal to 0, so E3 is equal to h cross omega 31. Now the Schrodinger equation that describes the evolution of the system is given by this time dependent Schrodinger equation, I h bar del k psi. K psi represents the quantum state of this 3-level atom, and on the right hand side you have this Hamiltonian. There are two parts in the Hamiltonian. One is H0, which is the bare Hamiltonian, that is the Hamiltonian without the presence of the fields, and then when the fields are present, then this interaction part of the Hamiltonian would be there. All these are operators, and this is the Schrodinger equation we are having, and V is the V is the interaction Hamiltonian, which is coming due to the interaction of the atom via the dipole moment and the electric field applied. E of T is the total electric field that is applied to the atom, and we are going to assume that this atom or this bunch of atoms that we under consideration, atoms are uh, placed at a distance at a position say z is equal to 0. Okay, this is at a location z is equal to 0. So that's the reason I am not writing E of zt, rather I am writing electric field as a function of t. And again, as you can see, this is a semi-classical picture here, semi-classical treatment I am taking, because the electric field is treated as classically and the dipole moment is taken quantum mechanically. And in the next class onwards, we will actually start discussing the quantum nature of the electromagnetic wave as well. There, this electric field is going to be considered as an operator, but that we are going to discuss in the next class onwards only. But for now, we are doing the semi-classical treatment. And the state of the quantum system, this is represented as kth psi. It is going to be the superposition of all these eigenstate, say C1 kth1 plus C2 kth2 plus C3 kth3. Kth1 kth2 kth3 are the eigenstate, and C1 C2 C3 are the corresponding amplitudes. And if we put it in the Schrodinger equation, then we are going to have I h bar delta C1 delta T kth1 plus delta C2 delta T kth2 plus delta C3 delta T k3, that is on the left hand side, and on the right hand side we have this Hamiltonian h naught plus v into kth psi, which is C1 kth1 plus C2 kth2 plus C3 k3. Okay, now please note that the eigenvalue equations associated with these eigenstates are h naught kth1 is equal to E1 kth1 and h naught kth2 is equal to E2 kth2 and h naught k3 is equal to E3 k3. All right, and now if I take this equation and if I take the inner product of this equation on both sides by kth1, that means if I multiply by this kth1, let's say this is my equation number 1, if I multiply on both sides of equation 1 by bra1, then this is going to give me, as you know, you are going to get I h bar delta C1 delta T, because of the fact that kth1 bra1, this one is going to give you the only non-zero, because you know that kth1 bra1 kth1, this inner product scalar product is equal to 1, and kth1 kth2, this scalar product is 0, and kth1 kth3 is equal to 0. Because of this, you are going to have only one term on the left hand side, and on the right hand side you are going to have E1 C1 plus C1. Now you are multiplying this by kth1, right, on the right hand side as well. So therefore you are going to have C1 1 V1. Okay, then you are going to have another two terms, C2 kth1 V and 2. Okay, and then C3 1 V3. So all these are operators. These I can write in a short form like this: I h bar delta C1 delta T is equal to E1 C1 plus C1. These are basically the matrix element of this interaction Hamiltonians, V11 plus C2 V12 plus C3 V13. So this is what I obtained. Now please note that the matrix element of the dipole moment operator mu is going to have these elements. So you know that it is mu11, mu12, mu13, mu21, mu22, mu23, then you have mu31, mu32, mu 3 3 because it is a 3-level system, so dipole operator is going to be a 3 by 3 matrix. Once again, please keep in mind that we are considering this lambda configuration here, where the electric field, a probe field is applied between 1 and 3, and a pump or a control field is applied between 3 and 2. Transition between 1 and 2 is dipole forbidden, and because of the parity issue, you already know that the diagonal elements of this dipole matrix element is going to be 0. Okay, and off diagonal elements, because of the transition between 1 and 2 is forbidden, so mu1 2 is equal to 0, mu1 3 is non-zero, mu2 1 is 0, and mu2 3 is also non-zero, then mu3 1 is also non-zero, mu3 2 is also non-zero. Okay, all these are, there are going to be 4 elements, non-vanishing elements in the dipole moment operator would be there. So what I can therefore write, I can write this matrix element V11, that is equal to minus mu11 dot, this is operator element, then this is the total electric field, and this is equal to 0 because mu11 is 0. And similarly I have V12, and that is mu minus mu12 E of t, that is equal to 0. So these matrix elements are going to be 0 for the interaction Hamiltonian, and moreover we have already set that E1 is equal to 0, and because of this, as you can see, this equation will be left out with only one term on the right hand side, and that is going to be IS bar delta C1 delta T is equal to V13 C3, or I can write it as delta C1 delta T is equal to minus I by H bar V13 C3. So this is the evolution equation I get for the first energy level in terms of the probability amplitude, and similarly we can write the evolution equation. You can easily work it out, or we may actually do it in the problem solving session. You can derive the evolution equation for the second energy level and the third energy level as well, and these are going to be of this form. On the right hand side here, you are going to have minus omega 21 C2 minus I by H bar V23 C3, and the third equation, evolution equation, would be delta C3 delta T is equal to minus I omega 31 C3, okay, minus I by H bar V31 C1 minus I by H bar V32 C2. So these are the equations that you are going to get. So let me write all these evolution equation once again for the various energy levels in terms of the, or various states, state 1, state 2 and state 3 in terms of the probability amplitudes. So these are the equations from which we are going to eventually work out the density matrix equations. However, first you please note that V13 is equal to this matrix element 1 mu dot E. E is the total electric field. Okay, this is what you have. Now, by the way, this dipole moment operator is nothing but the charge of the electron and the distance, right? So displacement. So this is the dipole moment. So therefore I can write V13 is equal to minus E x13 dot E of t, where this x13 is nothing but 1x, this is the position operator basically, 1 3. And similarly we can write V23 is equal to minus EX23 dot product with the electric field, and V31 is equal to minus EX31 dot E of t. The electric field is the sum of the probe and the control field, control or the pump field. As you can see here, that we are writing only the temporal part of the probe as well as the this control or the pump field, because of the fact that we have already assumed that the atoms are located at the location z is equal to 0, and here EP cap is the polarization of the probe field and EC cap is the polarization of the control field. Now if we put this expression for the electric field in the evolution equation for the probability amplitude C1 time evolution equation, here if we put the expression for the electric field, then we can obtain this particular equation in a very straightforward manner. Okay, now if we define two quantities called the Rabi frequency omega for the probe, here the superscript p represents the Rabi frequency for the probe, and here the superscript c represents the Rabi frequency for the control field or the pump field. If we define the Rabi frequency like this, and just recall that Rabi frequency in the context of the two-level atom, we defined it as mu dot E divided by twice h bar in an earlier class. So in the similar line here, because there are two fields, one is the probe field and the control field, we are having two Rabi frequencies corresponding to the probe and the control field, and then in terms of these Rabi frequencies we can finally get the evolution equation for the probability amplitude in this form. So this is our equation number 3, we are naming it, and in the similar fashion we can have the time evolution equation for the probability amplitude C2, as well as we can write the time evolution equation for the probability amplitude C3. So equation this 3, 4 and 5 gives us the time evolution equation for the probability amplitudes. Now it's clear that in the absence of the radiation fields, that means when the probe and the control field are 0, then the corresponding Rabi frequencies are also going to be 0, and this will result in the time evolution equation of the probability amplitude. They will take this form, these three equations you are going to get, and the solution of these three equations are trivial, because the as you can see from the first equation, delta C1 delta t is equal to 0. That means the probability amplitude is constant at all time. That means whatever it is at the initial time t is equal to 0, it's going to be the same for all time. Similarly, this from the second equation you can trivially get that C2 of t is equal to C2 of 0 e to the power minus I omega 21 t. Omega 21 is the, as I have already told you, that's the transition frequency between the energy level 1 and energy level 2. And this again CT, this amplitude, probability amplitude for the third energy level, and C3 is going to evolve like this: C30 e to the power minus omega 31 t. Omega 31 is the, as you can see from this diagram, omega 31 is the transition frequency between the energy level 3 and 1. Please note that omega p, which is the probe field applied between the energy level 3 and 1, that may not be exactly equal to the transition frequency omega 31. It may be slightly detuned, and similarly omega 32 is the transition frequency between the energy level 3 and 2, and omega c is the control field or the pump field applied between the energy level 3 and 2, and here also omega c may not be exactly equal to omega 32, it may be slightly detuned. Okay, anyway, so these three solutions that you have seen here, it inspires us to take the answers in this form. So we are going to assume that C1 is equal to C1 tilde. We are changing the variables here because that way we will be able to simplify our equations further. And the logic behind these answers is we are taking it purely because of these solutions that I have just discussed. So similarly, C2 is C2 tilde e to the power minus omega p minus omega ct, And if you just look at it, omega p minus omega c, if you just look at this diagram, omega p minus omega c is nearly equal to omega 21, because omega 21 is the transition frequency between 2 and 1, and omega p minus omega c is nearly equal to omega 21, and that's the reason here instead of omega 21 here we are putting omega p minus omega c. So I hope you see the logic here. And similarly omega 31, as you can see, omega 31 is nearly equal to omega p, so that's why instead of omega 31 here we are putting omega p here. So this is the answers we are taking and putting these answers in our equation number 3. So this was our equation number 3 for the time evolution of the probability amplitude C1. And if we put these answers there, it's very straightforward to see that we are going to get these equations in the new variable delta C1 tilde. In the new variable we are going to get this time evolution equation. And here you see there are several terms. For example, if we look at this particular term and if you look at this particular term, these terms are oscillating with very high frequency because it is oscillating at twice omega p, it is oscillating at omega p plus omega c, and these highly oscillating terms we can neglect, and then we'll be left out with this particular equation here, because of the we are neglecting all the highly oscillating terms. Okay, and this term also highly oscillating, so we are neglecting all of them, and then we will just left out with this particular equation. So that way we have simplified our time evolution equation for the probability amplitudes. Similarly, putting the answers in equation 4 and 5. So equation 4 and 5 already I have written here. So yeah, you see this is equation number 4, which gives the time evolution for the probability amplitude C2. Equation 5 gives the probability amplitude for the C3. Okay, I think you will be able to get more benefit from this class if you also sit with pen and paper and follow the calculations along with me. If you write it down on a piece of paper and work it out, then it would be you will be able to follow this particular class very easily. Now putting these answers in equation 4 and 5, we can again obtain this evolution equation for the probability amplitude for the second energy level, as well as the probability amplitude for the third energy level in terms of Rabi frequencies and new variable in this fashion. And if we now define, because you see there are this particular quantity is sitting there and here this quantity is sitting, so if we just define two parameters called the detuning parameter delta 1 is equal to omega 21 minus omega p minus omega c, you can easily make it out that omega 21 is nearly equal to omega p minus omega c, right? You can figure it out from this particular image also here. And similarly delta 2, another detuning parameter, it is equal to omega 31 minus omega p. That is what I was saying, that omega 31 may not exactly matches the probe frequency, transition frequency between 3 and 1 may not exactly match the probe frequency, it may be slightly detuned, and that detuning is given by this parameter delta 2, and similarly the detuning parameter delta 1 is defined. Now in terms of this detuning parameter, we can now write the evolution equation for the probability amplitude C2 and C3 in this fashion. So we are having these three equations. By the way, now onwards what I am going to do is that I am not going to write this tilde sign anymore. C1 tilde I am going to write it as C1, C2 tilde I am going to write it as C2, and C3 tilde I am going to write as C3. So these are the final equations I get after doing all these simplified assumptions or calculations, so to say. So these are the evolution equation for the probability amplitude in terms of the detuning parameter and the Rabi frequencies. However, as you can see here, we are not yet have written the density matrix equation. These are the equation in terms of the probability amplitude only. By the way, another assumption we are going to make here is that we are going to assume that the control field exactly matches the transition frequency, control of the pump field exactly matches the transition frequency between 3 and 2, as you can see from this diagram. So if we take omega c is equal to omega 3 2, the transition frequency between energy level 3 and 2, then what we are going to have is this. It is going to simplify our things further. You see, our first detuning parameter delta 1 is omega 21 minus omega p minus omega c, and omega 21 is basically the energy difference between the second energy level and the first energy level, omega 2 minus omega 1 in terms of frequencies. This is the difference. Similarly, omega 3 2, I can write it as omega 3 minus omega 2. Thereby, as you can see from this equation, we can easily write omega 3 minus omega 1, which is nothing but omega 3 1, and omega 3 1 minus omega p is nothing but the detuning parameter delta 2. So if we take that the pump is exactly in resonance with the transition frequency between 3 and 2, then both these detuning parameters are equal, and let me take that delta 1 is equal to delta 2 is equal to delta, only delta. And under this condition, then I can write the evolution equation for the probability amplitudes finally in this particular form. Now we are going to write down the density matrix equation, and you know the density matrix equations, for example, rho 1 2, rho 1 2 is nothing but c1 c2 star, right? And therefore if I take the time evolution, time derivative of that, then I get this one, this equation. Then putting delta c1 is equal to this from the evolution equation, and delta c2 is this part, c2 to delta t is this. Of course, the complex conjugate I have to take, and then from here it is trivial to see that you are going to get this density matrix equation for rho 1 2. And then if we consider the probe field to be sufficiently weak compared to the control field, and that's what the thing that I already mentioned you, that compared to the probe field, the pump is very strong and probe field is sufficiently weak. In that case, this equation I can write delta rho 1 delta t as this, where I have ignored because this probe field is very weak, because probe field strength of the probe field is going to be given by this Rabi frequency. So I am ignoring this, and if I ignore that, then I am getting the density matrix equation for one of the components of the density matrix element, that is rho 1 2. I can write it in this particular form. Again, you can proceed in the similar way. Delta rho 1 3 delta t is going to be this. Then again putting the equations for delta c1 delta t and delta c3 star delta t, I can put these equations here, and thereby I get the time derivative of rho 1 3 in this particular form. Okay, so these are the density matrix equation I am writing here for two elements so far, density matrix element rho 1 3 and rho 1 2 here, right? These are the two equations that I have written so far. Now if we assume that there is a excitation is very weak, under weak excitation approximation, I'm going to explain what I mean by that. I can take rho 1 1 is equal to nearly equal to 1. That means that all the atoms are going to be in the ground state only. Very few atoms are going to get excited to the higher energy level. So in that case, I can say that the population is nearly equal to 1. So therefore at all times, so that's the reason I can take rho 1 1 is nearly equal to 1, and rho 2 3 is going to be equal to 0 because of this weak excitation. The density matrix corresponding to rho 2 3 is going to be 0 at all time. Similarly for rho 2 2, rho 3 3 as well as rho 3 2, If rho 2 3 is equal to 0, if we take, then obviously rho 3 2 is also going to be 0, and rho 2 2 is the population in the energy level 2, and rho 3 3 is the population in the energy level 3, and we are assuming that these energy levels are hardly getting populated, very few populations, so they are going to be nearly equal to 0. And under these circumstances, you see in the density matrix equations we are having 6 terms, right? Basically 9 terms. It's a 3 by 3 matrix, and out of these 9 elements, already you see this 1 2 3 4 5 elements you are already having. So you just need to bother about two elements only, that is rho 1 3, because if rho 1 3 you know, then rho 3 1 also you know, because rho 3 1 is equal to rho 1 3 complex conjugate. Similarly, if you know rho 1 2, you know rho 2 1 also, because rho 2 1 is the complex conjugate of rho 1 2. Okay, so density matrix equations are the only two equations you need to bother about it, that is rho 1 3 and rho 1 2. These are the coherence terms in the density matrix. And by the way, so far while we are writing this density matrix equation, we are not bothering about the damping issues, but already we have discussed it in our quantum master equation class and otherwise also, that this coherence terms eventually decay, and this decay or damping has to be taken into account. And if we take that this coherence, say rho 1 2 decays at the rate gamma 1 2 and rho 1 3 decays at the rate gamma 1 3, then it has to be included in the density matrix evolution equation phenomenologically we can add. So we are adding this damping term here, that this coherence rho 1 3 is decaying at the rate gamma 1 3, and similarly rho 1 2 is decaying at the rate gamma 1 2, and therefore these are the evolution equations we have to modify, and therefore finally we are getting our density matrix equations in this particular form, and this is what we are going to use now. First of all, let us find the steady state solution of these equations. By steady state I mean that you have to put del rho 1 del t is equal to 0 and del rho 1 3 del t is equal to 0, because after waiting for long amount of time, these density matrix elements are no longer going to evolve. So that's the reason you can put the left hand side of these equations to be 0, and if you do that, then this is what you are going to get in the steady state. And then from the first equation you can find out rho 1 2 trivially, and from the second equation then you can get rho 1 3. Now using rho 1 2 in the expression for rho 1 3, you can obtain an expression for the density matrix element rho 1 3. And if you remember, in the beginning of the class I told about the significance of rho 1 3. I hope you remember that. So we can work out to rho 1 3 in terms of various parameters like the Rabi frequency of the probe as well as the Rabi frequency of the control field. What is interesting to note here is that this density matrix rho 1 3, it can be controlled. This matrix element can be controlled by using this pump field or the control field, right? Because of the presence of this term in the denominator, omega 3 2 for the control. Okay, now this steady state, let us now go to find out the steady state electric dipole moment P at the probe field frequency. And you know that you just have to take the expectation value of the dipole moment operator, and the dipole moment operator you can find out by taking the trace of the rho into mu. The dipole moment operator, rho is this, there are total 9 elements, but as I have already discussed, because of the weak field excitation approximation, rho 1 1 is equal to 0, rho 2 2 is 0, rho 3 3 is 0. Basically you are going to have only 5 elements that is non-vanishing in the density matrix. And mu, this also we discussed earlier, that mu is going to have all these terms. and therefore you can see that if you take the matrix product of rho and mu, and then if you take the trace, then you are going to get this expression, that P is equal to, P is, let me remind once again, that is the steady state electric dipole moment. So steady state electric dipole moment is going to be given by this expression. All right. So you can basically focus on one density matrix element rho 3 1, then dipole moment element mu 1 3, and then the other part is simply the Hermitian conjugate. By the way, you please note that rho 3 1 is the originally it is C3 C1 star, and but we have in between we have done the change of variable. We have taken C3 as C3 tilde e to the power minus I omega t, and this is what you should actually get here. This is what I have written. And also, as you have seen, that ultimately what we did, we just rather than writing the tilde, we wrote C3 tilde is equal to C3, and C1 tilde is equal to C1. So these particular points just have to be kept in mind. There should not be any confusion, and this is the reason this e to the power minus I omega pt term is appearing in the expression. So this dipole moment expression at the steady state is simply this expression. I hope it is easily understandable to you. So this is what now we are going to use. We have to now put the expression for rho 3 1. Rho 3 1 already we have worked out here. Actually, we have worked out rho 1 3. So because rho 3 1 is nothing but the complex conjugate of rho 1 3, so if we take the complex conjugate of rho 1 3 and put it in the expression, then we'll be able to get the expression for the steady state polarization P as this expression, right, that is written in the box. And omega 3 1 is this expression, the Rabi frequency at the probe, for the probe. Also note that this polarization P is actually, this polarizability is proportional to the applied electric field, and this is equal to, is proportionality is equal to the so-called polarizability alpha E that you know from your basic physics course. So utilizing this, because now we are concerned about the polarization between the energy level 3 and 1, so that is happening due to the application of the probe field. So therefore this complex polarizability at the probe frequency, the probe frequency is omega p, so that's the reason I'm writing P is equal to alpha omega p EP. So don't get confused with the earlier alpha that we have written earlier, which we actually denoted for absorption, but here this alpha of omega p represents complex polarizability at probe frequency. Then electric field at the for the probe is EP. So if I write down the full expression for EP, then this is what I get, right? And here EP is the amplitude of the probe field. So utilizing all this, if I just write the left hand side of the equation with this one, this is what I have written here, and on the right hand side I have this expression here, and if I equate both sides, I am not bothering about the complex conjugate, so the complex conjugate is going to be anyway equal to each other, so therefore just focus on only one term on both right hand side and the left hand side. Then this is what I get. I'm sure it is easy to understand. And if you are, as I have already suggested, if you are taking a piece of paper with you, these calculations are though lengthy, very straightforward. So equating both sides, you get this expression, right? Because e to the power minus I omega pt is appearing on both sides, so it get cancelled out. Now what I am doing here, because of the presence of the EP cap, which is the polarization of the probe field, I am taking the dot product with EP star. Why EP star? Because you see here EX31 is there, here X13 is there. So if I take the complex conjugate of this matrix element X13 or X31, So that's the reason I'm putting it here, EP star. On also because of the fact that I know that EP star, EP cap star and EP, if I take the dot product, it is equal to 1. So utilizing that fact and as well as utilizing this fact, now here this quantity is simply mu13 and this quantity here is mu13 star. So product of this is nothing but mod of mu13 square, and using these two facts, one is this one and other one is this, we can obtain this polarizability, complex polarizability expression like this. It's a complex polarizability, that means it has a real part as well as an imaginary part. I hope you have understood this far. Now recall that this polarization is related to the electric field via this expression epsilon chi e, and again this is equal to, polarization is nothing but number of dipole moments per unit volume. So this is what you have, n alpha omega pe, and from here you get the expression for the chi, that is the susceptibility, and you also know that the refractive index is associated with the susceptibility. This is the refractive index at the probe frequency. It is related to the susceptibility via this expression 1 plus chi, and from there you can have the refractive index as seen by the probe frequency is this one, and it's a complex quantity because alpha of omega p is a complex quantity. So you can figure it out, the real part of the refractive index and the imaginary part of the refractive index. First of all, there is another quantity which is of utmost importance to us, is the absorption coefficient. And absorption coefficient, as I have discussed earlier, you can figure it out that this is related to the imaginary part of the refractive index, and eventually it can be written via this expression. The absorption coefficient at the probe frequency is related to the polarizability, imaginary part of the polarizability at the probe frequency. So that one you can get, and then if you put the expression for the imaginary part of alpha omega p, then you can get this particular expression here. And similarly, you can make out the refractive index, which is the real part of the refractive index also can be worked out, and the real part of the refractive index would be given by this expression. Now one thing immediately you can see that if this detuning parameter delta is equal to 0, then the refractive index is equal to 1, because you see here this whole term is going to be equal to 0 if delta is equal to 0. You can see that very easily. So refractive index is going to be equal to 1. And what about the corresponding absorption? The absorption coefficient is going to be given by this expression here. Now generally, if the control field is very strong, if it is this Rabi frequency is much larger than these decoherence rates gamma 1 to product of gamma 1 to gamma 13, then what can be seen here that this absorption coefficient can be very small. What it means is that a sufficiently intense pump field can induce transparency at the probe frequency. You can make some plot. For example, you can use this expression for the absorption coefficient A of omega p, and you can plot it in the unit of A of omega p. You can write it in the unit of n omega p mu13 mod square epsilon c h bar. Then that is actually easy to do that. Just you have to take this whole term to this side, and you can write it in terms of the A of omega p in the unit of, that's what I mean by this. Then you will be left out with only this particular expression. You see, you will be only left out with this particular expression only. And if you take gamma 1 2, this decoherence rate, decay rate is equal to 0.02 of gamma 13, and also if you take the control field to be absent, that is it is the Rabi frequency 0, then you see that there is going to be absorption at the resonance, that is at delta is equal to 0, you are going to have absorption only. But if omega 3 to the control field the Rabi frequency is taken to be 3 times that of gamma 1 3, and also if you take gamma 1 2, this we take it as to be 0.02 into gamma 1 3, then you see you are going to get the absorption the coefficient versus detuning parameter. If you plot detuning, you are plotting in the unit of detuning versus gamma 1 3, that is in the normalized unit, because detuning has the unit of frequency, gamma 1 3 is also has the unit of frequency. Then if you do that, what you see is that at the resonance the absorption coefficient is 0, that means there is no absorption at all, and this pump field or this probe field can propagate through the medium without getting absorbed at all. So what does it mean? It means that for realization of EIT, the decoherence rate gamma 1 2 has to be small, and also you see from this analysis that EIT basically arises from the coupling of this rho 1 3 element of the density matrix, and rho 1 3, as you know, it determines the dipole moment at the probe frequency, because the probe is applied between the energy level 1 and 3, and it couples if rho 1 3 is coupled to the off diagonal density matrix element rho 1 2, and if rho 1 2 is non-zero, it is not equal to 0, and rho 1 2 is atomic coherence, and therefore EIT can be attributed to this atomic coherence rho 1 2, and because of the presence of this atomic coherence EIT happens. And also there is another way to look at EIT, that it can be interpreted as a quantum interference effect. What I mean by this is simple to understand. You see, the atom can go from the energy level 1 to energy level 3 via two paths. Now absorption takes place when the field is applied to the atom, and this field energy is used to take the atom from the ground state to the excited state, and then the field is not able to pass through the medium because its energy is basically utilized in pumping the atom from the ground state to the excited state. Now quantum mechanically speaking, there are two parts. The atom can go from the state 1 to 3 via two parts. One part is part 1, it can go directly from 1 to 3, and another part is that it can go from 1 to 3, then 3 to 2, and then 2 to 3. Because the path 1 and 2 is dipole forbidden, it cannot take that path. So if these two paths interfere destructively, then the probability that the atom can go from the state 1 to state 3 vanishes, and thereby we say that the probe field is not getting absorbed. That means for the probe field the medium appears to be transparent, and this is the essence of electromagnetically induced transparency. And here also you see that it is basically induced by the presence of the control field. I hope you got a fair bit of idea about what electromagnetically induced transparency is. Let me stop here for today. In this lecture, we have discussed the phenomena of electromagnetically induced transparency in great details. The lecture became a bit lengthy because I wanted to show you all the mathematical steps behind EIT calculations. However, as regards examination is concerned, you need not have to bother about all these mathematical details. Rather, you just have to focus yourself to the concept behind EIT. In the next lecture onwards, we are going to treat electromagnetic radiation as a quantized object, because so far in this course, we are treating electromagnetic radiation classically and the matter quantum mechanically, and that's the domain of semi-classical regime. But in the next class onwards, we are going to treat electromagnetic radiation also quantum mechanically. So see you in the next lecture. Thank you so much.